皆様お待たせいたしました。本日はアーキテクチャカンファレンス2025にご参加をいただきまして誠にありがとうございます。それではただいまより Booking.com BV SRE マネージャーアディティア・セス様にご登壇をいただき、Booking.com 流 MySQL のスケーリンググローバルティブでの運用最適化と題してご講演を開始いたします。それではアディティア・セス様、どうぞよろしくお願いいたします。So could you come up to the stage, please? 大きな拍手でお迎えください。
Hello, Tokyo. First of all, thank you, Findy.com, for bringing me here. It's a so nice place to be here. I represent Booking.com, and ouch. Thank you. Sorry for that. I'm here from Booking.com on a talk about scaling MySQL at Booking. To give you a context, we are one of the world's biggest MySQL users, having more than 10,000 servers. And to be honest, I have to give you an insight, a confession. We actually break our databases every day, every single day, on production. We use so much of our insights on queries and things. It breaks our system every day. What we do is we run some capacity test on your production instances, the customers' queries. They break our servers every day. And I would take you to a journey on how we make sure that those breaking things are actually useful for us, and how we saved up to 60% cost just by breaking our servers on production. So here is the thing. One thing which I would like to say is our mission. Our mission is making it easier for everyone to experience the world. But at Booking, it also means a lot of technical complexity. But first of all, some questions. How many of you have used Booking.com before? Please raise your hands. Thank you so much. How many of you have used databases? Okay. But this is the hardest part of what my questions are. How many of you actually know the cost of your systems, cost of your infrastructure? Okay, cool. But I think after this talk, you would actually go and check the cost of your infrastructure. Let me take you to that journey. So who am I? I'm Aditya. I'm SRE manager at Booking.com for MySQL team. I have in total 19 years of experience working at different development and leadership areas. I love scaling systems, and I'm passionate about ROI of infrastructure at scale. I'll take you to the journey, and this is the part, right? We will look on the challenge of running one of the world's biggest MySQL infrastructure at scale, defining what exactly is good for what we do, a case study that I would take you, how we run capacity tests at scale, the impact it brings, achieving twice the performance, but less than 60%, lowers the 60% cost. Also give you some key takeaways that you can use just after this talk, and some Q&A after the talk. So let's go on the challenge, running one of the largest MySQL instances. Here you see how big our MySQL scale or our Booking scale is. We are in so many countries, 6.8 billion users. Booking's done so far. Huge amount of data, huge amount of limitations that we have, huge amount of complexity we have. And this is a big challenge to solve. So how do we solve it? On 4 databases, we use MySQL as our main data store. And what it means is it's traditional. A single primary but tens or hundreds of replicas which goes behind this primary. We are multi-cloud in terms of bare metal, our own private cloud, and also public cloud. We are multi-region. We always make sure that even one region goes down, we are still up and running. We have a huge amount of infrastructure, different MySQL clusters, more than 100 million queries per second at peak. And the most important part is that we do own database infrastructure, but we don't own data or queries or tables or schemas. We just own the database infrastructure. That's very important. This is our typical setup, the classical replication setup in which how MySQL could be scaled up. You have a single primary, but below that primary you have multiple replicas, and we actually use this setup to scale up to 1,000 servers in the past. The tree keeps on growing, and you see on those green boxes the application servers. Application is very close to the database. It belongs in the same region, and a primary could be connected from an application across region. So what I represent is kind of site reliability for databases. It's database reliability engineering, that what we do. And it's just a set of tools and practices like an SRE, but for databases. And what we do is manage database infrastructure. We provide servers, we provide guarantees, and I'll show you how. And we provide scale based on future growth. We also provide database expertise in cases when it's required by teams who want to work with different bottlenecks that they see. We do participate in on-call rotation, which is very important. Even because of a user or an application, if something breaks on production, a database is involved. We are there to support. And we also deliver database observability across the whole value chain. So all the SLOs and SLI about database is adhered. Okay, let's take you to the next part of the journey, which is defining good. How we use the SLIs and SLOs. So SLIs is site level indicators, so service level indicators. SLO is service level objectives. I hope people know this, but these are the metrics that these are the KPIs for a reliability team like us, which is what we are measured on. Let's go deeper into that. So database performance is very sensitive to each user. You can have users affecting this performance. For example, full table scans is actually a long-running process. Non-indexed, complex queries, these are slow and expensive. Database as a queue is sometimes being used by many of our applications, which is creating many issues like locking or timeouts. People do read from primaries. We try to avoid that as much as we can. We ask them to use read replicas for reading and write only on primary. For example, bulk update or delete causes replication delay, and so on. We have many such cases which affect performance, which affects database scales, and these are just a few of them. So we thought of, okay, let's get some SLIs because our reliability team needs to have some SLIs, service level indicators, to say if the service is performing well or not. So we ended up, first of all, picking up something and then rejecting those things. And I'll show you why. So we reject query latency. Why? Because we cannot control it. It's based on users. If they run a query which is non-performant, the latency would be high. Infrastructure team like us cannot do that or control it. Throughput. How many queries are running at the same time? It's also can't be controlled by an infrastructure team like us. It is the responsibility of a team who owns the application running these queries. And also the replication delay. replication delay is the count of how much delay is between a primary and a secondary or a replica. And we can't control it. It's based on user queries. If somebody runs a big insert or an update, your replication delays go high. So if you cannot measure it correctly or you cannot control it correctly, you cannot improve it. So for us, we created something different. And why? Because these are some things like buffer pool size or CPU usage. This doesn't affect in real terms. Customers actually need page to be seen. They don't care about these numbers. So what we ended up using was, in place of query latency, we took read availability. In place of throughput, we took write availability. And in place of replication delay, we took replication running. And we choose these because we could actually control them. And we could also measure them easily. And I'll show you how. So we designed an application which is called as MySQL Availability Reporter. What it does, it just acts like an application, nothing else. It just do some very cheap inserts and really very cheap selects across the infrastructure. So you see two different regions here. And the availability reporter application is deployed across all the regions. It completely mimics our applications, does some writes, does some reads, monitor them, stores these values, and we aggregate them over a period of time, and we see exactly like how is our SLI or SLO working. And this is how we see it on our dashboards every week, every month, and we monitor these numbers. Here you see on your leftmost side, you see read availability, which is 100%. You see write availability in the middle, which is below 100%, but you see the yellow line, which means that it didn't breach our SLO. Our SLO here is 99.7 for write availability. For read availability is 99.99. This is an internal metric which we were comfortable with, and we gave them. And same for replication running. So we could have those initial blips of performance degradation, but it doesn't break our SLO, so we are fine. And one important part is the gap. What you see between the green and the yellow line is the error budget we have. And we are authorized to use our error budget to break our systems. And I'll show you how we do that. So some key takeaways from this part of our journey. You choose SLIs that are 100% under your control. And decide where it makes sense to measure those SLIs. So try to mimic how actual application or a user load is coming so that it's tied to the user or an application. And one big key takeaway, don't follow on 100% SLO. Never do that. I mean, unless and until it's too cheap to do that. Because otherwise, you would not be able to break that or take some decisions which are easy to take for a small cost. And yes, always use your SLO budget. So the next part, I would take you to the case study. And this is actually very, very informative in the sense that what we discovered just with the data that we had for so many years. Capacity test on production. So how we break things on production. Exactly what you are using Booking. I mean, you might be part of those production tests that we run. So before that, we also see a lot of toil, which is for our ops teams, typical. Things like server provisioning. We have to always create these servers. Imagine 10,000 servers, more than 10,000 servers actually, across different platforms, across different regions, data centers, cloud, and whatnot. We need to provision, configure, make sure that they are compliant. It's a big thing. things like schema splits. You have big database, you split into smaller parts. Password rotation, grants, so many other things like this, yeah. Upgrades is a big part of us. Yeah, and so on. So many other things, yeah. So our approach to get this on running is relentless automation. We keep on automating things. We target more than 90 to 95% of all things being automated. And reliability is being our top priority. We choose proactive work over reactive. We find bottlenecks before they actually happen. And yes, our fleet grows faster than the number of developers we have. So why we automated our capacity planning? We avoid any risk by automating our capacity, our number of servers. We do cost control and scalability. It's really important at our scale. We want to automate it. The evolution of different hardware profiles, it's needed on the workloads that we have. We also run analytics, things like horizontal scaling, forecasting. And it's critical for our keeping the lights on. It has to keep on running. There were some design decisions we took. Scheduling at peak capacity hours. Why? Because we want to stress test on the maximum point of the day where we see traffic. We run against our production fleet. This is needed for us. We also have a kill switch wherein we can stop the capacity test if we are required to. And we prioritize business continuity over cost efficiency. So if we have to choose one, we have to choose business continuity. And then let's look on the building block. It's called as MySQL pool. And just bring some attention here because this is important for the rest of the presentation. A pool is a set of servers, part of the cluster, which gets the similar load. So if you are using Booking, you might be going to a pool which is prioritized for customers. There might be another pool which is prioritized for other workloads like crons or your OLAP analytics workload. And those could be slow. So we do this to avoid noisy neighbor situation and make things better for the whole fleet altogether. So our capacity test is brought into 3 phases, and I'll also give you a diagrammatic understanding of that. So our test phase is simple. We choose a machine to get more traffic, and then we run capacity test on that machine. So this machine, among other machines, is getting more traffic, more queries. And then this machine pushes some values of what is it experiencing in terms of different metrics that we record. The second phase is the calculation, wherein the calculation happens. We have an application called as target size calculator, which reads on this capacity metrics. And then on scaling, we just use those new metrics to create the number of servers required. And this is how it looks like if I have to show it dramatically. We slowly increase the weight. What is the weight? Weight is like the percentage of queries going to a server versus the other servers of the same pool. And there are some termination conditions. For example, for us, it's CPU, the disk I/O, and the number of connections. We keep on checking this every few seconds, but we keep increasing the load every 15 minutes till the time we either break the server or we maxed out our trials. We cannot break the server. And this is how it looks like. So you see a primary which finds one of the pool in each region, and it schedules a capacity test. You know, the capacity test is now running on each different region. We want to check metrics of each region separately. And then we read these metrics into Graphite, which is our internal database for these numbers. And then we start doing calculation. So we have this application target size calculator, which reads its metrics every 24 hours and also reads the previous values for last 7 days. We create some average, we do multiplication, some internal metrics that we have, internal algorithm we apply, and then we push the new target size back to Graphite. The scale phase is wherein we actually use a different tool for adding these numbers. And based on the difference, we add the provision. There is another tool which is provisioning manager. So just think of these are small applications, very small applications, which are just growing or shrinking the number of servers. And what you have seen, just to brief you, is we ran this capacity test. We found a new value of what is actually required based on stressing just one server for each of these 3 regions. And now we have a different number. And then we scale it up wherever it's required across whole of our area. And now you see from 3, it became 4. So from 3, it's now 4, right? It's actually how we see it. So here you see the blue line, which is the capacity test result, and the yellow line following it, which is the actual number of servers. And this is how we track it. And this is an informatic of the whole fleet, how the capacity tests are looking. This gives you an idea of how many capacity tests were run. And this is a metric that we also look. If it's breaking a lot, you have to fix it. Let me take you to the most enticing part of the presentation, which is how we use these capacity tests to actually save huge amount of cost and increase our performance of these servers by a good factor. So we use capacity test. In the previous slides you saw that we were using capacity test to actually scale horizontally. We were adding the same type of server more and more. But for some cases, we actually scaled up to 900 plus instances. That's insane. And then we had to do a lot of things on MySQL to make sure that happens. Like we wrote our own code on top of MySQL to make sure that happened. So cost optimization is a big factor at system at scale. But we thought, can we use capacity tests to optimize this? And what happens was, so when we looked on horizontal scaling, the problem is always like we have to find the same type of server, keep adding them one by one. And the breaking point was always like operational cost was heavy. It's like more toil is required from people. Data center space was constrained. Our energy consumption went high. So we thought, rather than doing horizontal scaling, can we do vertical scaling? And we digged into some numbers. So this is a graph which is showing you the data of multiple years of whole of our fleet, whole of our MySQL fleet. So think of 10,000 servers. And mostly what we see is our CPU on an average was just being used 10%. And this is very low. We were wasting so much of resources. However, when you see this, our memory was reaching its limit. And why you don't see 100%? Because we limited 80% of MySQL pool usage. So we were kind of using the whole memory. We were evicting cache and not using the CPU, paying for it so much. So, I mean, we built a hypothesis around this. And the hypothesis was, do we always need horizontal scaling? Can we do some vertical scaling on RAM? So we added some servers which were having 256 GB RAM and ran against our production fleet because we could use just the capacity test manually and use these servers for some of our target selected chains, some clusters which was really huge. And what we saw, any guess? What do you think would have happened? If you think, would it bring us down in terms of scale? That is actually what happened. So you see on the left, we were 125 servers. Those were 32 core, 32 vCPUs, but 128 GB RAM. From there, we came to a new type of server, which was the exact same CPU, but twice the RAM. And from 125, we reached to 56. That's more than somewhere around 60% lower number of servers. But that's not the big part. We also were surprised to see the next one, which is this one. We actually saw our CPU usage also go down because of that. Because we took, why? We were not using that much cache eviction, which happens on MySQL. So one thing is that our workloads are more read heavy, not write heavy. So we do more than 100 times the reads as compared to the writes. And that indicates it, why we need more RAM on MySQL. So we did a deal with our server team. We ran similar tests first on many of our biggest MySQL chains. And we measured the server usage on infrastructure, similarly with capacity test. We found that majority of our applications or application databases would gain by adding more RAM. And maybe they need less CPU. So we agreed with our server team to get more suitable hardware. And this is very important if you see this. Sorry, I had to hide the exact database names and things. And also, you see column EFGH. This is actually real data, but I had to hide it. Sorry for that. But this is maximum what I could show in the conference. We are a public listed company. You see different databases there. A previous configuration of servers on column C, and D is the new one. What we did actually was we just doubled the RAM mostly. In some cases, we had to shrink the size of SSD because we could. And the percentage of cost reduced. You see only the 20 numbers, but we had more than 100 chains which we tested. The average we saw was a drop of 60% cost just by doing this. And the good part was that we didn't lose any other feature like latency or other things which is required by our applications. So in many cases, we were actually faster than before and cheaper, both at the same time. And the impact was obviously huge. So because of this, we actually moved to private cloud. So from exactly like big bare metal servers, we are embracing private cloud. We built our own private cloud. And we found that for us, 1:16 CPU ratio, CPUs to RAM ratio makes complete sense. And with our private cloud, we can actually have different variety of hardware, variety of virtual machines with different configuration of RAM, SSD, and CPU. And we also are able to evolve better. We saw some VMs actually was saving 90% of the cost. But still, they were either same or better than before. We also see this based on different guardrails that we have placed. So we could test different hardware sets. We could test different virtual machines on production just because we have this capacity test. And it's easy. It's easy for us to fail. So the result, which I already told you, the result was that we got more than 60% of cost with better or similar SLIs for our workloads. And so I would just also bring you some key takeaways from this presentation, if you have followed me along, which you can actually use in your company. So 4 key takeaways that I would like to present here is, visibility. It's really important to have visibility, which is much, much easier for each person in the company to have visualize. It's not the responsibility only of a site reliability engineer or a platform developer, but each developer in the company to be able to see what's going on and use things like that. In our example, you saw we use capacity metrics, we visualize that data, and we could find the bottleneck of RAM versus CPU. If we didn't have this data of past so many years, we would not be able to get this insight. Also, there was also talk in the morning about vertical versus horizontal scaling, and I completely agree with that talk. And also, from my experience, only horizontal scaling is not good. You need to always think about a mix of both. Once you reach a critical horizontal scale, people should think of also adding vertically. I mean, horizontally scaling hundreds of instances is always not a good idea, I would say. And there is a sweet spot in between of horizontal and vertical. So there has to be a mix of these, and people should be aware of that. Also, things like modern hardware in cloud, I mean, they bring cheap gains. You could just take it. Also, testing on production is really, really important. If you can do that, most of your problems are solved. Obviously, it's complicated. It's hard to do in the first time. But once you are done, you have full visibility, full control of trying out new things, also breaking things. Remember, you have SLO budget that you can break things. And we use SLO budget to break things on capacity tests. Sometimes these capacity tests actually fail, but we are within our limit of SLO budget. And also smart hardware changes. So for our example, the cost of RAM was super cheap as compared to a new server. So it's just 2 or 3% of the cost of a server. And we actually needed less servers just because we added that 2 or 3% on a subset of that big set of servers. So think about this deeply. I mean, in your case, it could be something different, not just RAM, maybe network or your disk or CPU. So what should you do if you are on cloud? Most of you, I think, are on cloud, not like Booking. So Booking started 20 years ago, and for that reason, we have our own infrastructure. Cloud were not present there. But on cloud, you have a lot more options, much faster. So the journey that I took us around 2.5 years to conceptualize and run it on production. Right now, we are upgrading to those systems. But for you, doing it on cloud, it just takes a few hours. So on cloud, check your infra usage. If you are on AWS, which is most popular database, use CloudWatch, performance benchmarks, also infrastructure monitoring. Please try to find bottlenecks, and you know most about your application. So try to think about where your application goes from and which parts. Which part can break, which part can sustain. And try to optimize on each part separately. So, for example, network, memory, CPU, these are the things which are very basic, but there could be something different on your system. It could be a third-party service. Test on different hardware profiles. So I'm currently speaking based on the experience that I have from Booking. I'm leading a hardware team, which is also responsible for the software it runs on top of that hardware. If you are working with such logics or in such a specific similar setup, it could be also not just database, but also your application. You have to try out different hardware profiles. For example, if you are aware of AWS, you have instances like R-type instances, which have RAM 1:8. You have C-type instances, which are faster for CPU, but less on RAM. There are I-type of instances, which are giving you more SSD performance. And i7-IE, for example, which is the newest system that they brought, is giving you more SSD, but less of CPU as compared. X-type instances have 1:32 type of instances. So one CPU, 32 GB of RAM per CPU. So think of those things. Gravitons are really good. If somebody has problems with Graviton, please let me know after the talk. But Gravitons for us, running on RDS, for example, they make very nice sense. They are cheaper and faster, both at the same time. So yeah, and every few months, please repeat, because you would just gain by doing nothing. I mean, not changing your application. You don't have to always look on the code to change something. So you don't have to optimize your code. I mean, you can just do this on hardware. It's so easy. Every year, AWS releases new type of instances. I mean, more than a year. So I mean, more frequently, multiple months of a year, they would have something new coming in. So our duty as a developer or a platform engineer should be able to go and see, hey, something new is there. Can I optimize that? And just thinking that way, what we ended up doing in our booking infrastructure, we bought AMD EPYC servers because we are also on-prem company. AMD EPYCs, they were like beast. Previously, we were using Intel. So I have no affiliation with AMD or Intel. But for our case, we got huge gains while applying those AMD EPYC servers for our private cloud. The CPUs are twice as fast as our previous old systems. And the RAM that we applied was in a factor of 1:16 and also faster. It gave us huge economies of scale. We also pay less for our electricity cost. So yeah, think about these 4 items if you're on cloud. I think most of you are on cloud. And that's it. Please, arigato. This is, I think I wrote it correct. And please, if you love Booking, if you have used Booking, please apply to us. This is our site, careers.booking.com. Please apply. There is always an opening somewhere. We are having offices across the globe. We need good technical people. Please apply there. That's my email if you really want to. I'm sorry for the first 5 minutes because I wasted your time, but sorry for that. Also, I would love to have you on LinkedIn. Please connect. Please ask me any questions if you cannot ask today, and let's be connected. And in the last comment, I would like to thank Findy. And you guys are great, so thank you for inviting me here. This is my first time in Japan. I hope I was clear enough for you guys. Maybe I was too fast in some cases. But for any confusion, please, I'm standing there. I would be also here tomorrow. Please reach out to me for any questions that you have. Thank you so much.
ありがとうございました。Thank you for joining us today. Thank you very much. 今一度大きな拍手をお送りくださいませ。アディティア・サス様、どうもありがとうございました。